is here, because if you want to solve it, you need to first of all take moments around this equation to find what the reaction is, and then take moments of these two forces around this point to find, I mean, it is some work, right? But I can tell you, you can try to do that, and you'll find that the numbers we just calculated are all correct. They correctly represent the influence line, which will take a long time to do otherwise, okay? So one more time, what did we do here? We had a frame. I want to find this moment. So I do exactly like before. I relax the support so that I can create a rotation so that this guy, NA times 1, I want times 1 here. Because then any other unit load I have will produce a work minus 1 times y is equal to 0. So NA will be, that means this value will be equal to the value of MA. Okay. Okay, if you're not convinced, let's try to prove. For example, taking moments around this point. If I would have a unit load here, taking moments around this point, if this is 1, I have 1 times 3, there is a total moment of 3 around this point. So therefore there must be a reaction here, which is 3/4. 3/4 times 4 will create a 3 moment like this, 1 times 3 will create a moment like this. This is 0. Right? And if I take moments, now around this point, I have 3/4 times 8. Okay, moments around this point. 3/4 times 8 will give me 6, and 1 times 2 will give me another 2. So the total moment is 8, and the counteracting moment must be 8. It's correct. But I don't need to do all the static analysis. It's very fast. It's very efficient. I just calculate simply how this frame will move. Let's do one more. The same frame, I want to calculate, for example, what the influence line AY will look like. Okay, let's do it. Okay, I want to find the influence line for AY. What do I need to change? I need to let this move up and down. So I must change my support here. I will change the support at this point to be this type of support. That means like a slider, but which does not allow rotations. Okay, it cannot rotate. Okay, so slider, it cannot move horizontally because I don't want AX to work. I want only this reaction here, this reaction AY, I want the only one to produce work. Okay? So I change this support, I have it like this now, with this, with this. Right? And what we do, because I want to produce to produce AY times 1, I will assume that this moves up by unity. That means I impose that I want to move up by 1. So first of all, let me find where is the center of rotation. For this body, where is the center of rotation for this part here? This body can only slide up and down, it cannot rotate. If it cannot rotate, you understand, the center must be at infinity. And it must be infinity in this direction. And because it can only do this thing, it can only slide up and down. Right? And if this is at infinity, from infinity to pass to this point, it means this line, and this line. The second center of rotation is O2 here. One more time. Okay, I change this support because I want this force, I want to produce work since I want to find its influence line. So I change, but I don't want to create work for here. That means I should not allow rotations. I should not allow this type of movement. So this is the type of support which allows that. And then what I will do, I will assume now that the structure moves with centers of rotation O1 at infinity here, and O2 must be here, right? I will impose a rotation of a displacement of 1. If this moves by 1, this will move by 1 clearly. This will move by 1 clearly. If this moves by 1 and this distance was 4, this rotation here will be 1 quarter. Right? So this here will be 1/2. This here, vertical movement 0. Horizontal movement is 1 quarter times 3 quarters in this direction. The rest of the points here, no horizontal displacement. They don't have horizontal displacement. So we have 2 influence lines, one for the vertical loads. For the vertical loads, this moved up 1, 1, 1. Sorry, 1, 1. And this is only half. And this here, vertical didn't move at all, so this goes down to 0. So this is the influence line for vertical loads. That means if I would have a vertical load here, the work done would be AY times 1 minus 1 times Y. So AY times 1 minus this 1 times Y should be equal to 0. So AY is equal to Y. If you put a unit load here, all the load is picked up by this support. That's what it says. If I put a vertical load, this reaction will be automatically 1. If I put the load between here and here, then it will vary from 1 to 0.5. All positive. That means if I put a vertical load here, indeed the reaction will be upward. If I put between here and here vertical load, it will vary from 1/2 to 0. For example, if I tell you that if I put a load here at the midpoint, it will be 1 quarter. I found all the reactions immediately. And if I have horizontal movements, if I think about the horizontal movements, this point did not move, none of these points moved horizontally, right? Because this was only sliding up and down. So all these points did not move horizontally, right? This point did not move horizontally. This point moved horizontally. This moved horizontally from 0 here, this didn't move horizontally, to this, which was 3 quarters. So if I have a unit load here, this is the only part where we have influence line. That means if you put a unit load right here, there will be a vertical reaction here of plus 3 quarters. Plus, because the load was in this direction and the movement was in the opposite direction. So it's positive. Right? We said whenever, if I assume for such a unit load, what is this the influence line for a y? So this unit load, this movement is in the opposite direction, so it creates work minus 1 times 3 quarters plus AY times 1 is equal to 0, so AY is equal to 3 quarters. It will come automatically. Alright? Okay. Let's do. Okay. So you can easily prove that if I put here a horizontal load of 1, this vertical reaction will be 3 quarters. Indeed, actually we proved it here because when I put a unit load here, this was 3 quarters down. From sigma effect, sigma y, this must be 3 quarters up. It's correct. Right? That's much faster than doing the static analysis, right, to calculate everything for different positions. Okay. Okay. All right. Let's. Any questions here? It's okay. Okay, I will ask one of you to help me. Okay, for example, one last example with this and then we move on. Let's say we want to find the influence line for Gx. The question is, find the influence line for Gx. Okay, what are we going to do? Since I want to find for Gx, this is, first of all, this is a stable structure already because it has two parts. Pin here, center of rotation here, center of rotation here. This is the common point, they don't lie on a straight line. It is stable. Now we go here. Right? We want to find Gx, so I must relax this because I want to introduce some rigid body movement. So I will relax it and I'll make this an unstable structure by removing relaxing a little bit this boundary condition, okay? And I will assume now that this is a mechanism, it can move, and I will assume that this here is equal to 1. I will introduce a movement of 1, so that the work done is Gx times 1. Okay? Now, we think about the center of rotation. The center of rotation here is O1 here. This is a common point. So the center of rotation must be here. If this distance was 3, this is 3 and 3, right? So this is 4 and 4. This must be 4. If everything correct, right? Because my drawing is not perfect, but this is equal length 3, 3, 3, 3. Okay, this is 45 degrees. Okay? So this is at 4. This is up here. Okay, if this is up here, this distance was 2, so this distance was 6. So it means this point rotates by an angle of 1/6 to make this equal to 1. It means now all we need to do is tell how different points move. Okay, so this point will move 4/6, so 2/3. This point will move upward, right? Because 1/6 times 1.5, that means 0.25 movement upward. 1.5 over 1/6 times 1.5. Right? Okay, this point will move horizontally 2/3. Vertically will not move. This point will move horizontally 2/3. It will move down 1/6 times 4 will move down 2/3. Okay. If this movement is 2/3 and this distance is 3, that means this rotation here must be let's see, 2/9, because 2/9 times 3 will give me 2/3. Okay, it will be the correct horizontal movement. So 2/9 is this rotation. 2/9, that means this movement here is upward 2/9. Horizontally, everything 2/3. Okay, that's it. I know how every point moves. And now I just draw the influence line. I will draw one influence line with green color for the vertical load. So I assume I have vertical load. So vertical, I have to see how everyone moves. This moves upward, 2 nines, right? This did not move at all. This moved 2/3. So it is a straight line like this. Okay. These values here are positive because the work done will be minus 1 times this distance. Okay, so when I move the right, it will be plus. This here will be negative values. Okay, because when I write the equation, I will say ax times 1, this guy produces work, plus 1 times this distance of y is equal to 0. So ax is equal to minus this number, whatever this number is, with a minus. So whenever the load moves in the same direction as the displaced thing, it is negative. So plus 2 9 minus 2/3. Vertical movement here 0. Vertical movement 0.25. So this is again it will be a straight line, right? That's it. Okay. So for vertical load, negative values, positive values, negative 2/3, positive 2/5. That's what it is. Okay, the influence line. For the horizontal load, if I would have a horizontal load, let's say to the right, if I have a horizontal load to the right, this point moves horizontally 2/3, and assuming that the load is like this would be negative 2/3, because the movement and the load is in the same direction. So the work done is ax times 1 plus 1 times this is equal to 0. So this is a negative value. When I write the work, I'll say 1 ax times 1 plus 1 times this distance is equal to 0. Right? So this distance y is equal to minus ax. So this point here we have 2/3, here I have 1. So it is a load like this. Again, because it moves in the same direction, this is also with a negative value. So this is minus 1, minus 2/3, 0, minus 2/3. This is for horizontal movements. What kind of reaction? That means if I apply here a horizontal load, then this reaction here will be minus 2/3. If I apply a load here, it will be minus 1. If I apply a load halfway here, in the middle of this column, it will be half of 2/3, 1/3. All the values, gx, yeah, gx. And this is the influence line for gx. So 2 influence lines, one for vertical loads, one for horizontal loads. For vertical loads, this line. For horizontal loads, these 2 lines. If I ask the question, what is the, if I ask the question, where should you place some, we have a vertical load of 10 kilonewton per meter, okay? Where should you put your load, your vertical load, to create the biggest positive reaction here? If I want to create positive reaction, I must put my load everywhere from here to here, because these are all positive influence lines. From here to here, so as long as I load this part and this part, I create the biggest possible reaction gx to the right. If I put my load between here and here, then I create the biggest possible reaction to the left. Right? Because no matter where you put the unit load here, it creates a left reaction, as you see, because all these values were negative. Right? This brings me back to the point where I think we talked about this in the tutorial, but let me repeat it. If we have an influence line, if I have a distributed load, W of x, and I have some influence line which looks like this, right? And if I apply if I apply over this interval, this distributed load, over this interval, this is the influence line of some quantity, the influence line of some reaction R, okay? The total, due to this distributed load, the total reaction is the integral of the influence line, let's call this y of x, the influence line y of x times w of x times dx. This integral is the total reaction. Why? Because if I consider a small element here, dx, this is equivalent to having a load w of x dx. Due to this w of x dx, due to such a load, if the influence line is y of x, this load y of x dx creates a reaction which is so many times the influence line, because for unit load we know the reaction is y of x. For load w of x dx is w of x dx times y of x. Right? For unit, if I would have a unit load here, the reaction would be so much. Now I don't have unit load, I have w of x dx, so the reaction is so many times bigger. But this is just due to this part. If I want to sum up all these contributions, I would have to have the integral over x. Okay? Now, if this is a uniform load, if this would be a uniform load, then the W0 can be placed outside, and what we get is that the reaction is the strength of the distributed load, so W0 times integral of y of x dx. When this is when w of x is equal to W0, if it's constant. If you have a constant load, then if I tell you, I put here, if I ask the question, for this beam, for example, I tell you, I put a unit load, a uniform load of 10 kilonewton per meter. Can you calculate what this moment was? Okay, you're going to tell me. The moment here is 10 kilonewton per meter, is 10, times the area under this diagram. Based on what I said here, the reaction is the integral of the distributed load times the influence line. It's the product of these two diagrams. If one of these diagrams is constant, then I can pull it outside and I will have the constant times the integral of the diagram, that means the area under the influence line. For example, here, if I would tell you this building, for example, is subjected to a distributed load of 20 kilonewton per meter. Calculate this reaction. You're going to tell me immediately the reaction R, the reaction Gx, this reaction, right, is the distributed load 20 times the area under this diagram. This is a negative area because these are negative values. So, times 1 plus 2/3 over 2, that's the average, right? Times the length, which is 2. And all this with a negative value. Because my values here were negative, the area was negative. So the distributed load 20 times this area, which is the average of these two sides, times the length, which is 2, 2 and 2 cancels. This is 5/3. So this is minus 100 over 3. It's minus 33.3. Immediately I calculate the reaction due to such a distributed load. I tell you how much reaction we will have at this point. We'll do more examples, okay? If I tell you we had a vertical load, I want to create the maximum reaction Cx. The maximum negative reaction. What is the biggest force in this direction? It is when we load from here to here. Right? Because this all give negative values. Okay? If I put here, I create reaction in this direction. If I want to create a maximum reaction to the left, it means I must load between here and here. If my distributed load is, let's say, 40 kilonewton per meter, the maximum I could do is to load all the way from here to here, and the result would be 40 times the area under this triangle. Yeah. Sorry. I assume that this one, I assume it's applied on this leg, for example.
But then, if you apply this influence line on AC.
AC.
Yeah, just one.
Yeah. What did I say here?
But then you use the adhesive to calculate the reaction.
No, I want to calculate the maximum moment here, right? Okay, this is, sorry, I use this one. Sorry, I got lost. What? Okay. You have a problem with what? With the 20, right? Let me see, what is the 20? This number, right? Yeah, this is wrong. Not 1 plus 2/3. Sorry. This would be true if I would apply here the load. Sorry, for this load, right? For this load, right? For this load, because and for this load and for this reaction, GX, right? I mixed two examples now because I start. Okay. I think it's clear what we are saying, but let's do one more example, okay? You're right, here I applied the load here, but instead of taking this triangle, I took this triangle. That was my mistake, right? So it means we assume that the load was on this side. Basically, the idea is you construct the influence line, and if I ask you for a uniform load to calculate the reaction, you take the intensity of the distributed load times the area under the influence line. Right? Clearly, I did a mistake. Thank you so much. Okay. Now we calculate the influence lines. Okay, this was, I hope it didn't confuse you. I did a little calculation mistake there. Okay. In many cases, we're interested to find the influence line not for a reaction. For example, we might ask the following question. I have this beam. And I ask the question, I have a unit load that travels here, but I want to find the influence line for, let's say, the bending moment at this point. The bending moment at this point. That means when I put the load here, clearly I have a bending moment. Or I have a shear. Or I have an axial force. And I want to know, as this load moves, how this bending moment becomes, when it becomes maximum, minimum, etc. Okay, so I'm going to talk now how we deal with problems where we don't ask what happens to the reactions, to the influence line of the reaction, but we want to find some internal moment. Okay. For example, A, B, C, D, E. I want to find about the point F, which is at the given point, at the midpoint or at some other point. Now, if I want to do that again, I would have to, with statics, I would have to say, let's assume it's at the distance of x, and try to solve as a function of x, what is the moment mf here? That means the moment here, there is a moment here. I would have to find it using equations of equilibrium, right? And I would have to do many cases. One case when x is between here and here, one time when the point is between here and here, too many cases. We don't want to do that, we want to use the same approach. So we are going to think about some rigid body motion, right? So that what we want now is, I want this forces here not to create any work. I don't want any of the reactions to create any work, right? Because, but if there is a force mf here, a moment, for example, mf, I want those to create work. So what I will do, we will go to this point, which was one point of the beam, and I'm going to assume that we have a hinge for a minute. Because putting a hinge, again, separates the bodies, separates into more bodies, 1, 2, 3 bodies now. And these bodies, if I can make them move in a certain way, then this works, these forces, these moments will produce work. Okay? All right? Okay. So what I'm doing, I introduce this artificial. Let's put some numbers here again. Let's say 2, 4. Let's say 3. Let's say 4. Okay, whatever. Some numbers. Okay. So I introduce a new pin, right? Now instead of before it was a stable structure. We can easily prove it. It had two bodies with one center here. The other one had the center to be here and here. It's impossible, you know. And so it was stable. So now we relaxed a little bit. We put an internal hinge. So now the structure will become unstable. Right? So which are the three bodies? Body 1 has clearly here the one center. Body 2 clearly is here the other center, right? And body 3 clearly here must be the other center for body 3, okay? Body 1, this was a pin, so it must be this one. It must lie here and here, so it must be this one. If this is the one, then here, this must be, all 3 must be there. Okay, so these are the centers of rotation. And now I will assume that this rotates. It rotates. That means if this rotates somehow, and this would come something like this, right? Then this would be something like this, right? This would be all the way like this. Okay, that means the displayed shape would look something like that, right? The question is, I have to tell you how much. So I say I will create a rotation, this in this direction and this in this direction, right? If I call this rotation here theta 2, and if this rotation here is theta 3, right? Then the work done, and if I have some external load, whatever, let's say a unit load 1 here, all right? Who is producing work? This guy did not produce work, this did not produce work, this did not produce work, right? The shear forces here, the shear force here and here, they don't produce work because this moves upward, and this is downward force but moves upward, so one creates positive work, one creates negative work. The shear forces will not create work during this movement, right? When I have this shear force and this shear force, they produce opposite work because both points moved the same amount upward. One was pushing upward, one was pushing downward, so they didn't produce work. But this moment will produce a work mf times theta 2, mf because it rotates in the same direction. And this mf on this side produces a work mf times theta 3. Right? And the external load, if this is y for example, will produce a work minus 1 times y is equal to 0. So the question is now how to choose theta 2 and theta 3. So what we get here is that mf times theta 2 plus theta 3 is equal to y. So if I make theta 2 and theta 3 to be equal to 1, if I make the sum of these two angles to be 1, then the shape I will get is exactly the same. If this is equal to 1, then the value of MF is exactly equal to the deflected shape. So what does it mean? Okay, if this angle is theta 2 and this angle is theta 3, it means this is the angle theta 2 plus theta 3. It means we want the relative angle between these deflected shapes to be 1. Relative angle, okay? This rotation compared to this rotation, relative to each other, the two bodies must have a relative rotation of 1. Then the total work produced is mf times 1. mf times 1 minus 1 times y is equal to 0, so mf is equal to y. So all we need to do is create a rotation here where this is equal to 1. Okay? All right. Okay. So to find now we'll see how in this particular example how we can find all the values. Okay. All right. You understand that if this theta 2 and theta 3, this will be theta 2 times 4. This will be theta 2 times 3. This will be theta 3 times 4. I mean, everything is in terms of theta of the thetas. Right. Okay. So I want this angle to be equal to 1. So this angle to be 1. The distance from here to here is 4. It means that this distance, from here to here must be 4 if I would project this line, because this angle is 1. So based on what we said, 1 times the angle gives you this side. This is true for very small angles, but again, because we will scale back, we assume that this is true. So when the rotation is 1 and the distance 4, this distance must be 4. If this is 4, and due to this distance must be 3/7 of 4. 3/7 of 4, because this starts from 0, it goes to 4 at the distance of 7. So this is 3/7 of 4. I found everything already, so that means 12 over 7 is this movement. 12 over 7, I can tell you what this rotation is, I can tell you what this rotation, I can tell you everything. This is 12/7, this is 4/3 times 12/7. This is the same. Okay. I found all the values. One more time, I'll do another example. So, one more time. We introduce a pin at the point where we want to find the internal moment. And we assume that we want these moments to produce positive work. So this part must move in this direction, this must move in this direction. But I want the relative angle. The relative angle is the angle between this new deflected shape, that means this angle here. I want to be 1. Because the total work done is mf times this rotation, mf times this rotation. So mf times this rotation plus this rotation, which is this relative angle, is the external angle of the triangle. So mf times this angle, if I make this angle into 1, then I get mf is equal to y. Let's do one more, okay, so you can see. Find the influence line for the moment MF. I want to find the influence line. There is a moment here. When I put the unit load, There will be a bending moment here. find for different positions of your load how much is MF. What do? We introduce at this point another hinge, right? Okay? Now we have three bodies. Body 1 from here to here, from here to here, from here to here. Body 1. What can you say about body 1? Center of rotation or stable or something? Stable completely. Okay, number 1 is stable, doesn't move. It means for number 2, which is this body, this is O2. If this is O2, this is a common point, then this must be O3. Okay? Now, I want to find the bending moment here. So I assume the bending moment is in the positive bending moment like this. I will calculate the influence line for such moments. Okay? So what I will do, I will rotate this body here like this, and I will rotate around this body here like this. So the influence line must be this. This is the influence line. Assuming the load is like this, these are all positive values, and these values are negative values. But what I want the relative angle, that means this angle, I want to be 1. Right? If I want this to be 1, it means this value here would be 4. 1 times the distance of 4, this will be 4. And if this is 4, and let's say this point here is a distance of 1. Okay. If I want to find the point F with a distance of 1, this value here will be 1. So the value is 1. So 0, 1, 0, minus 0.25. One more time. The relative angle, yes. The relative angle is 1. The distance between here and here 4. Therefore, this must be 4. That means this is a straight line, right? If this is 4, this must be 1/4 of 4. Must be 1. Three. 1. This is 3. 3, okay. 1. 4 was all this, 1 was this, 3 was this. Okay, so correct. This will be 3. And this will be 1/4 of 3, so this will be 3/4. This angle should be 1. This distance is 3. My notation, I'm too fast. Okay? From here to here was only 3, so this distance must be 3. If this is 3, this is 1/4 of 3 is 3/4. If this is 3/4, and this is the distance is 3, this must be 1/4. It's correct. Repeat. Yeah. Okay. Okay. Okay, there are 2 ways of doing it. Okay? There are 2 ways. I'll show you both ways. One way is to say we have a rotation θ2 here, and this is a rotation θ3. I could say like this, we have θ2 and θ3. What should be true? θ2 times this distance, θ2 times 1, this height, should be equal to θ3 times the distance from here to here, which is 3. Right? We should have this. And also we should have that θ2 plus θ3 should be 1, because I want the sum of the 2 angles, the relative angle, to be 1. So I can solve from these 2 systems, and I can find how much is θ1. θ1 will be 1/4. Sorry, θ2. Sorry. θ2 must be 3/4, and theta 3 must be 1/4 if you solve the system of equations, right? That means the sum is equal to 1, and theta 2 times 1 is equal to theta 3 times 3, okay? I can solve and I can find these two angles. That means I could solve and tell you that this is 3/4 and this is 1/4. You see? I could do that in such a way. The important thing is, because these two angles, because of this condition, the work done is mf times theta 2 plus mf times theta 3 is mf times theta 2 plus theta 3. It's mf. The total work is mf times 1. By putting this condition, I made sure that the work done is mf times theta 2. This is this work, this moment, due to this rotation, plus mf, this moment times this rotation, theta 3, minus 1 times y is equal to 0. Right? But because theta 2 plus theta 3 is equal to 1, I can write directly from here that mf times 1 minus 1 times y is equal to 0, so mf is equal to 1. So this is the correct shape. But instead of doing that, another way, I'll just show you a second way, instead of trying to find how much this angle is and how much this angle is, I can do it in one step, and I will say the relative angle between this new line and this new line, that means this angle here, this angle must be 1. The angle must be 1. If this angle is 1, then, and this distance from here to here is 3, I saw 4 before, but it was 3 really. Right? From here to here is 3. Therefore, this height must be 3. From similar triangles, now this triangle and the small triangle, we can see that this here must be 1/4 of this value. So it must be 3/4. So either you're going to find the angles, because once you find the angle, if you know the angle is 3/4 times 1 is 3/4. You can find this height. This is another way. There are two ways. Either you're going to solve for the two angles, or you're going to do this relative angle and you're going to proceed in such a way. Both ways are okay. What do we want? We want to create a movement so only these forces produce work and the external load. We don't want this to produce work, we don't want to so we only change this and we make the hinge, because when we have a hinge we will allow for this relative rotation, so the two moments here produce work. And I will make the two angles to sum up to 1, so the total work is mf times 1. That's the whole idea. So this relative angle being 1 means that either you're going to tell me that this rotation and this rotation must be such that mf times this distance and theta 3 times this distance is equal, and then the sum of these two angles must be equal to 1. Okay, this is a set of equations to solve for the two angles. Or if you don't want to find the angles, we can go directly from here and say, look, I want the relative angle to be 1. This distance is 3, so this must be 3. If this is 3 from this big triangle, this small triangle, this must be 3/4. And basically at this point you already calculate the rotation. This must be 3/4 over 1, must be 3/4, 3/4 over 3. Okay, let's do one more. Okay, let's say I want to find the influence line for the moment at this point. Influence line for the moment at B. That means I put different loads, vertical loads, horizontal loads. I want to know how the value of MB changes. Now, I need to tell you, when I say MB, how do I mean MB? I mean, let's say in this direction, let's say this type of moment. I specify in which direction. Because if I tell you in the opposite direction, find the influence line for that type of moment, you will create different rotations to produce positive work. Okay? Alright, so how are we going to do that? We're going to do that by putting here a pin support, a hinge. Right? I'm going to put a hinge. I want to find this influence line for this moment. Right? And now this becomes a mechanism. Before it was not a mechanism, right? Before it was stable. Because we have two parts with two hinges here and a common point like this. We have 3 points, 3 members. So member 1, O1 is here. Member 2, O2 is O3 is here. And member 2 is on this line, must be on this line, and must be on this line as well. Let's put some numbers, okay? Let's say this is 3, this is 1, and this is 4, and this is another 1. Like this, okay? Okay? So, from similar triangles here, if this is 1 and 4, and this is 3, this must be 12. From here to here must be 12. Right? Because this is 3, sorry, it is 3 times bigger. Okay? 1 to 4, so 3 to 12. Okay? This distance must be 12. Okay? So this is the center, O2. Okay. Next thing, I want this is the left body, which belongs to body 1. I want the rotation clearly to be in the same rotation like this. So I'm going to assume here that I have a rotation theta 1 in this direction. Right? But if this direction is theta 1 like this, since this point must move horizontally, it means the rotation here will be in this direction, theta 2. Okay, what is the relationship between theta 1 and theta 2? Theta 1 times the distance of 4, right, must be equal to theta 2 times the distance of 12. Right? And during this rotation, this guy will produce work mb times theta 1. And this moment, in this direction, will produce a work mb times theta 2. So the total work will be mb times theta 1 plus theta 2. Right? So what I want to do, I want to make theta 1 plus theta 2 now equal to 1. So I can say directly the work done is mb times 1. Right? I want to write mb times theta 1 plus mb times theta 2. And then the unit load minus 1 times y is equal to 0. But if I make theta 1 and theta 2 the sum to be equal to 1, then I will get immediately that mb is equal to y. That means I must choose a special theta 1 and theta 2 so that the sum is equal to 1. But they also satisfy this relationship. From here, you can easily find that this number must be the number 3/4, and this number must be the number 1/4. 1/4 times 12 is 3/4 times 4. Okay? It's going. So from here, if you solve the system of equations, you'll find theta 1 is 3/4, theta 2 is 1/4. And if this is 1/4, this point. Now we just show how every point moves. 1/4 times 12, that means this moves here by 3. 3/4 times 4 moves by 3. Vertical, this doesn't move. This moves by 3 because 1/4 times 12. It moves down. It moves down. 1/4 times 3, 3/4. 3/4. Sorry. 1/4. 1/4 times 3, 3/4. I cannot say 3/4 times 3, right? Because this body belongs in body 2. It doesn't belong to body 1. I cannot say this rotation times this distance, right? I cannot say that. This point belongs to body 2, right? So, since the rotation was 1/4, this is 3/4, this is 3, and this is 3/4, okay? Once I know this is 3/4, I can tell you that the rotation here is in this direction. 3/4 over 1, it must be 3/4, this direction. It means this point moves up 3/4. This point moves horizontally 3. So everything moves horizontally 3, and this point don't move. And vertical, this moves 3/4 up, 3/4 down, this doesn't move at all. So the influence line is for vertical loads. For vertical loads, this didn't move vertically, so it goes down. It was here 0, like this. This is the influence line. Assume you have a unit load down, all these values are negative because it moves in the same direction, and this is positive. So positive 3/4, negative 3/4, and that's it for the vertical loads. For horizontal loads, if I would have horizontal loads, let's say to the right, acting here, or to the right, acting with this leg, this point moves to the left, so this is the influence line, all positive, because it moves in the opposite direction. And again, on this side, also all positive. All positive with a value of 3. 3, 3. Right? So the influence line starts from 0, it goes to 3. From 0, it goes to 3. This is for horizontal loads. Right? Assuming the loads to the right, these are all positive values. Positive values. Because the influence line is opposite direction than my load. That means if I put a load here, if I put a load in the middle here, and ask you how much is the moment here, for a unit load here, it will be, this is 3, it will be 1.5. For a unit, if I put a unit load here, the moment there is 1.5. If I put a unit load here, the moment here is 3. Plus 3, right? If I put a load like this of 30 kilonewton per meter over the entire right leg, the load, the bending moment NB, will be 30, the distributed load, times the area of this diagram, which is 1/2 of 3 times the height of 4. This is the value of MB. Okay, the distributed load was to the right, the influence line was positive, we start from 0 up to 3, so 1/2 of 3 times the length of 4, this is the area under the influence line, times 30 is the total moment MB. You can try to solve the problem with a uniform load here of 30 kilonewton per meter, and you will find that this moment here immediately is this number. If we want to find, if we have some vertical load, and I say, when do we get the biggest question? If I ask here, for this point could have positive bending moment or negative bending moment. I mean, positive means in this direction, it means we need to put bottom reinforcement, right? To calculate the bottom reinforcement here, I must create the maximum such moment. The maximum such moment is introduced when I apply my load only here. Because this is the only place where we have positive values of influence lines. If I want to find the biggest negative moment, that is the biggest moment which is in the opposite direction, that is, I must find the biggest negative value for this. I must load only between here and here, because then I get the maximum negative moment. Okay, we can, when you have a structure, the structure is supposed to behave for all kinds of different loads. And so you must be able to create the worst case scenarios. There could be a case scenario where you have loading, you require loading on the top, and another where you require loading on the bottom. Because you need to see different positions where you need to place your live load to create different scenarios. Okay, we will continue next time.